Alright everybody, in this video we're going to talk a little bit more about inverse trig functions. And here I'm going to discuss what happens if we compose trig functions and inverse trig functions. So here we're going to do function composition, which is when we take one function and put it inside another function. So we're going to look at composed expressions that either have an inverse trig function inside a regular trig function, like these two examples, or the other way around, a trig function inside an inverse trig function. So we're going to start out with some examples in this video where we have the same trig function as the inverse trig function, so sine of inverse sine or cosine of inverse cosine. And I'll start out with the inverse trig function on the inside. So let's suppose, for example, we wanted to evaluate the sine of the inverse sine of negative square root of 3 over 2. Well, this example we can actually just do by evaluation, okay, because the inverse sine of negative square root of 3 over 2 is something from the previous inverse trig function videos we know how to work out. Recall the inverse sine of negative square root of 3 over 2 has to be an angle between negative pi over 2 and positive pi over 2, so it has to be in the fourth or first quadrant. Its sine value has to be negative square root of 3 over 2, okay, and therefore that angle has to be negative pi over 3. And that's the angle that's between negative pi over 2 and positive pi over 2 with a sine value of negative square root of 3 over 2. Okay, so this becomes the sine of negative pi over 3, which is itself negative square root of 3 over 2. Okay, so note in this case we could almost think about the sine and the inverse sine as canceling each other out, and we'd be left with negative square root of 3 over 2. Okay, so now let's move over to this problem. We're trying to find the cosine of the inverse cosine of negative 8 over 5. Okay, so if we think about this problem, we want to try to approach it in a similar way to the problem that we just did. However, the inside isn't something we can evaluate because the inverse cosine of negative 8 over 5 isn't, something that is easily calculatable unless we have a calculator in front of us. But we want to think about, in terms of definitions, what this would be. Okay, so the inverse cosine of negative 8/5 is going to be some angle, theta, because inverse trig functions input numbers and output angles. That angle has to be between 0 and pi, and the cosine of that angle has to be negative 8 over 5. Okay, so let's think about this for a second. What is negative 8 over 5? Well, it's going to be negative 1 and 3/5. So, negative 1.6. Okay, but cosines are between negative 1 and 1. Okay, so in this case, we're trying to evaluate something on the inside that actually doesn't exist. Okay, because the cosine of negative, or the inverse cosine of negative 8/5 is not an angle that actually exists. We cannot find an angle whose cosine is negative 1.6 because cosines have to be in between negative 1 and positive 1. So here, there's no such angle. And therefore, there's no solution, or we could say the quantity does not exist. Is we have to be careful when we do these sort of trig function of inverse trig function problems, especially if you have the same trig function as you have the inverse trig function, because there's this temptation to just sort of cancel out and say, oh, the answer is -8/5. But that only works when the quantity on the inside exists. And in this case, since the inverse cosine of -8/5 does not exist, -8/5 is not in the domain of the inverse cosine, the quantity doesn't exist. On the other hand, if we replaced -8/5 with something that does exist, say -4/5, that's fine because -4/5 is greater than -1. So if instead we wanted to find the cosine of the inverse cosine of -4/5, -4/5 is -0.8, that's fine, that is between -1 and 1. Okay, so now the inverse cosine of -4/5 is, it's again, using the definition, an angle theta, where theta has to be between 0 and pi, and the cosine of theta is -4/5. Okay, and that exists. Again, we can find an angle. We would need a calculator to actually find it numerically, but an angle exists whose cosine value is equal to -4/5. And therefore, what we're trying to find is the cosine of that angle, because again, this inverse cosine is our angle theta, and we're told that that angle theta has a cosine of -4/5. So the cosine of the inverse cosine of -4/5 is just -4/5. Okay, so that's the first class of problem we have, where we have the trig function on the outside, the same trig function, but the inverse on the inside. And what you want to remember here is if the inside exists, then you can just do a cancellation. But you have to check, does that inside term exist? Inverse cosine of -4/5 exists because -4/5 is in the domain of the inverse cosine. On the other hand, we did -8/5, that did not exist because -8/5 is not in the domain. Okay, so now let's flip this around and we'll put the inverse trig function on the outside, but we'll stick with the same trig function on the inside as on the outside. Okay, so let's start out by looking at the inverse sine of the sine of pi over 7. So the thing you want to notice is we cannot evaluate that inside. Sine of pi over 7, we're not going to be able to find without a calculator. I strongly recommend when you do these problems, do not use a calculator because you won't be able to on the quiz or on the exam. So instead we want to think about the definition of our inverse trig functions. Okay, so remember that the inverse sine of some number, and the sine of pi over 7 is just, some number. Okay, we can just call that number x. So the inverse sine is going to be an angle. It's going to be an angle theta with two properties. Okay, the first is that theta has to lie between -pi/2 and +pi/2. Okay, so that is a necessary condition for an angle to be an inverse sine. The other thing we need is for the sine of that angle to be equal to what we put inside the inverse sine. Okay, that is to say, the sine of theta has to be equal to the sine of pi over 7. Okay, because that's what we were plugging into the inverse sine. Okay, so we're looking for the angle between negative pi over 2 and positive pi over 2, which has the same sine value as pi over 7. Okay, but that angle is just pi over 7. Okay, because pi over 7 meets both of those requirements. It's between negative pi over 2 and positive pi over 2, and it has the same sine value as pi over 7 because it is pi over 7. And therefore, the inverse sine of the sine of pi over 7 is just pi over 7. Okay, so here we see another situation where it kind of looks like the inverse trig function and the trig function cancel each other out. And they do to an extent. Okay, but just like with the last examples, we have to be careful about that and keep domains and ranges under consideration and don't just cancel the trig function and the inverse trig function out. So to show you why we need to be worried about that, suppose we did the inverse tangent of the tangent of 7 pi over 6. All right, so this is actually one that we can do by evaluation. We don't have to think too hard about definitions here. So let's go ahead and do this by evaluating the inside to start. Okay, so the tangent of 7 pi over 6, just to remind you, 7 pi over 6 is a third quadrant angle with a reference angle of pi over 6. It's pi plus pi over 6. So the tangent is going to be positive because we're in the third quadrant. It will have the same tangent value as pi over 6. So the tangent of 7 pi over 6 is 1 over square root of 3. Okay, or if you prefer to rationalize denominators, square root of 3 over 3. Okay, so this is going to be equal to the inverse tangent of 1 over square root of 3, which is not 7 pi over 6, but pi over 6, because the inverse tangent is going to be an angle between negative pi over 2 and positive pi over 2. So the inverse tangent has to spit out a first or second quadrant angle. 7 pi over 6 is a third quadrant angle, so the inverse tangent is never going to produce 7 pi over 6 as an answer. Okay, so in this case, we don't have this cancellation. We don't just cancel the inverse tangent with the tangent, and that's because 7 pi over 6, again, is a third quadrant angle, but for the output of an inverse tangent, we expect to see an angle between negative pi over 2 and positive pi over 2. Okay, but what I did here with the quadrants and reference angles kind of gives us an indication as to how to solve these sorts of problems. That we want to maybe think of an angle that is in the range of our inverse trig function, which has the same trig value as the angle that we're plugging in. So in this case, pi over 6 is in the range of the inverse tangent, and it has the same tangent value as 7 pi over 6. Okay, so for example, let's take a look at the inverse cosine of the cosine of 13 pi over 10. Okay, so now we can't evaluate this inside, again, unless you use a calculator, and we don't want to do it that way because we want to think about the definitions of the inverse trig functions. But cosine of 13 pi over 10 is going to be some number x. And the inverse cosine of x is some angle theta, because again, the inverse cosine always spits out an angle. And there are two things that are true. The first is that this angle has to be between 0 and pi, because that's the range of the inverse cosine function. Inverse cosine will always output an angle between 0 and pi radians. The other thing that has to be true is that the cosine of that angle is equal to the number that we put inside the inverse cosine, what I call x. That is to say, the cosine of theta is the cosine of 13 pi over 10. So what this boils down to is finding the angle between 0 and pi, so first or second quadrant angle, which has the same cosine value as 13 pi over 10. 13 pi over 10 is a third quadrant angle. Okay, it's going to be pi plus 3 pi over 10, so we have a reference angle of 3 pi over 10. We want to know what angle in the first or second quadrant has that same cosine value. Since we're in the third quadrant, the cosine value will be negative, which means the angle we're interested in is going to be in the second quadrant. And it has to have the same reference angle for the cosines to be the same. Okay, that is to say, the angle we're interested in is 7 pi over 10. So note that 7 pi over 10 meets both of our requirements. It's clearly between 0 and pi, and it has the same cosine value as 13 pi over 10, because they have the same reference angle of 3 pi over 10, and one is in the second quadrant, one is in the third quadrant, which means they both have negative cosine values. And therefore, the inverse cosine of the cosine of 13 pi over 10 is 7 pi over 10. Okay, so that is a little bit more complicated, but it really just comes down to knowing your quadrants, knowing your reference angles, and particularly knowing the range of your inverse trig functions. And whenever we have an inverse trig function on the outside, remember the result needs to be an angle, and it has to be in the range of that inverse trig function, in this case between 0 and pi. And if you remember that, then it will be a little bit more clear to see when you're doing cancellations and when you have to actually think about what's inside and how to replace it with an angle with the same, in this case, cosine value, where you can almost think about a cancellation. So we kind of think about replacing the 13 pi over 10 with a 7 pi over 10 because they have the same cosine value, and then you can almost think about doing your cancellation then. Okay, so that's going to be all for this video. In the next video, I will talk about what happens if the inverse trig function and the regular trig function are two different functions, like a sine and a cosine, or a tangent and a sine, and so on.